So what I'm going to talk about here is kind of our efforts on the multi-material additive manufacturing by integrating digital light processing and DLP approach. Certainly, before I start, I want to sort of thank my the group members, current group members, Xu Ruipeng and Liang Yue and Xiaohao Sun and Max Montgomery, and also former member Devin Roach. I think Shira and Devin contribute quite significantly to the work I'm going to talk today, and also other previous members. Also collaborate with Professor Renee Zhao at Stanford University, and also we have collaboration recently with Toyota North America. The multi-material printing is, in general, is highly desirable in additive manufacturing. As 3D printing first emerged, and we see these colorful kind of first statures from additive manufacturing, but they're all similar colors, right? So people quickly got bored. But if you look at the nature, we're doing things more, leaving a colorful world, and the birds have different colors. And also in most of engineering applications, we want to combine the soft material with tough material, with stiffer material to give superior mechanical properties. For example, nacre is a very good example, and that you combine this very soft proteins with very brittle ceramic, you can actually achieve very improved toughness. And here's another work we've done before with my colleague Glaucio Paulino, who recently moved to Princeton. We actually try to make tensegrity. In this case, we print the SMP rods and also attach that to the string that also 3D printed. We can attach them together to give this kind of self-popping up structures. And however, multi-material 3D printing is not so easy. I think we have seen quite a few talks today, early today, like Kevin did a wonderful talk using this multi-wet DLP printing approach. So we have been, it's very highly desirable also for 4D printing community, right? Because 4D printing, we typically can using different kind of polymers, soft shape mirror polymers or active polymers with inactive polymers to achieve shape change, right? This is early work that, done by Kevin. This is one of the first few papers published in 4D printing. In this case, we combine the shape mirror polymers with an elastomer matrix and to give this kind of shape changing. And also because of the 3D printing, we can nicely control the layout of different fiber, different materials. We can achieve very different type of deformations. That's very hard to achieve by conventional manufacturing approach. And this is another work by Dean, and also with Professor Martin Dunn and I, we're collaborating. This actually is we call direct 4D printing. You can directly print a structure that can either expand or shrink. But in general, multi-material 3D printing is not so easy. And as most of the additive manufacturing or 3D printing technology, it's not really suitable for multi-material printing. So our group, we try to develop different approach. One to the multi-material printing. One approach is to hybrid, and this is actually a machine we built about started probably 4 or 5 years ago. We tried to put different kind of printing methods together. This is actually funded by Air Force Office of Scientific Research. We put direct Inkwright fused deposition modeling inkjet, aerosol jet, and those photonic curing unit into one build platform. We also put robotic arms into it. So it's actually a very powerful platform, but it's very expensive. And this whole thing, we spent almost $400,000. We can achieve lots of interesting things. For example, you have this kind of printed ribbon, soft ribbon with conductive traces built in. So after printing, you can just plug it in. You can make it conductive. We can even print three-dimensional sort of conductive structures. But this is too expensive. So recently we started looking at low-cost approach. And one thing we're looking at, which we also work a lot on, it's called DLP 3D printing, right? DLP, I think Kevin had a very good introduction there. So essentially, and also Oliver get a good introduction there also. So essentially, you have a projector either coming from the bottom or coming from the top, right? Then you start to print a layer of resin, and either you move your build platform up. So this one I call a bottom up, basically the bottom layer going up. So it's a bottom up printing approach. This is actually that's what carbon 3D used technology. Advantage of this approach is you're actually using fewer resins because the resin reservoir is relatively small. And the other one is the top-down approach. Essentially, if you have bigger reservoir and the light coming from the top, so each time you print the layer, and then the build platform going down a little bit, so we call top-down approach. And in general, this DLP printing give you very high resolution. It's about 50 to 100 micron. Like as Kevin mentioned, they can achieve about 2 micron resolution. And also you print one layer at a time. So since we're using photopolymer, they can cure really fast. Typically, you cure each layer in about 2 to 5 seconds. And also you only have zip motion, right? So you save lots of motion, like XY motion, to make it very fast, and also low cost. So each one you probably can build a machine, for about in the lab you can build probably just $4,000 to $5,000. And right now you can buy from Amazon. They have even cheaper ones, probably just $500, $700. You can buy pretty good machines. The only drawback is just because you are using a single vat and you only print one materials and also one color. And as Kevin mentioned, they developed this very novel approach. They can quickly switching between different vats, so vat of resin, so they can print multiple a structure with multiple properties, which is very cool. Here, we're trying to do is try to hybridize another approach. It's called direct ink write. Basically, we try to put together digital light processing with direct ink write. Direct ink write, it's very similar to field stabilization modeling. The only exception is field stabilization modeling using thermoplastic filaments. Well, the DIW using a liquid resin. So so you basically extrude the resin into onto your platform, and then you cure them. And so we try, and also DIW is also a low cost approach, and you can get a DIW printer roughly also about $4,000, maybe even cheaper, $2,000, depends on the dispenser that you're using to control the deposition of the ink. And so here shows how we put these two machines together. And this is we're using a top-down DLP printing. So as we print the structure, this platform just start move down. If you want to do the DIW printing, I just lift this building platform up and move the DIW nozzle into the system, so I can read the system. I can read the ink, DIW ink into the structure. Advantage of DIW is, first of all, DIW is very compatible to DLP. So most of the DLP ink now you can print by changing the viscosity. You can just make them to DIW printing, and that's one advantage. The other advantage is that DIW can also allow you to print functional inks. For example, you can print conductive ink like silver nanoparticle paste, or you can print liquid crystal elastomers, which I'm going to talk later. And we also built made a homemade control software, so we can take the model, we can slice them, we can define which one using DLP print, which one using the DIW print. For the DLP print, we slice them into the images, and for the DIW print, we can generate the G code, then we can integrate them into a GUI, and then we can using the GUI to tell the machine which one we're going to print. And here shows the structure that we print. You can see we can print, this is a kind of Busby, which is a Georgia Tech sort of mouse code. And we can embed it into different kind of structures. We can print different kind of lattice structure with different inks. So here shows the interface between them. You can see here, DIW, typically the layer thickness, the nozzle we're using about 100 to 200 micron layer nozzle. So that gives us each layer is about, I think it's 200 microns thick. And so that's is incompatible with DLP print. So normally we put about 6 to 8 layers of DLP. We can print one DIW layer. But you can see the transition is actually pretty smooth because we're using the top-down approach. So after you print the DIW, you sink your printed structure into the resin reservoir, so the ink refill it, so it cover it. So you can see this here. We actually one DIW here, the other one DIW here. You can see the transition. So this is a DIW and this is a DIW. You can see a relatively smooth transition here. But certainly, the software need to calculate, how many layers of DIW we print, how many DLP layers. We need to do those kind of calculations. And we can also looking at the interface. Because like I said before, the DIW printing, essentially, you can just take DLP print ink, and then you can sort of modify the rheology. You can print them together. But certainly, you don't have that, not necessary to have using the same ink all the time. But in general, in both approach, it's acrylic-based photocurable polymer. So they actually have pretty good interface. In this case, we show this is DLP printed part, this is DIW printed parts, and you can see this interface. And we put in the ICM, you can see this is DIW layer and this is DLP layer. The interface, you can see it, but there's no visible, really some kind of gap or anything in there. You can just sort of then you can see, and this is another DLP. This actually is a silver ink. We print the silver paste into a DLP layers. You can see still there's no obvious kind of gaps between the two layers. Yeah, for the DLP and DIW printed, in our case, the DLP part is relatively soft. And so you can see when we do the interface, you can look at the interface is very good. When you stretch it, you actually break in the DLP layer, not really the DLP part, and not really the DIW part, because that means you have really very strong interface between the two material. Here shows a few printing that we can print the silver conductive ink into the printing process. You can see this is how we can print light tower. In this case, we horizontally print the big structural light tower. Then we're using leaf grooves. Then we can write this conductive ink to it. And after printing the silver inks, we can finish up the other half of the light tower. And so after printing, it's conductive, so you can plug in your LED, and so the things will light up. We can also design our code. We can actually print on a conical surface. This actually, we rewrite the G code, so we can actually print the structures. You can see it's continuous, just right helical line in the space. And then after printing, we can finish up another printing of the DLP, so we can cover this kind of helical conductive trace in these kind of structures. And we can also print a string gauge. In this case, we can using a very soft, we can using a very soft matrix, a relatively soft matrix. Then we leave the grooves here. Then we're using DLP, DIW to print the silver particle inks. We can print a string gauge. And so after printing, you can do the testing. This actually shows the resistance change during the during your cyclic loading of the string gauge. You can see here, and the string is actually pretty linear with what is the string change. And also, liquid crystal elastomer is kind of one of the well-known active material that's been using for 4D printing. Advantage of liquid crystal elastomer is that the shape change is reversible. So as you heat it up, and the polymer LC will shrink as you cool it down, it will expand. So typically, it is because you have this kind of molecular arrangement. So typically we call messaging, which is liquid crystals, right? So if you align them after your fabrication with LCE, at room temperature, they are aligned. And as you heat it up, due to the increase of temperature, the alignment actually lose their sort of alignment, become isotropic. So this is causing the shrinkage. So the DIW actually is perfect for printing of liquid crystal elastomer because the shear exterior sheening effect during the extrusion that actually can align the messaging. So that's a DIW is the most efficient way nowadays in printing the liquid crystal elastomers. So we can, with this approach, we can integrate liquid crystal elastomers into our DLP printing structure. So then we're using the DLP to print large box structure with high resolution, and then we write LC ink inside it, and then we can either embed it or we just leave it on the top. So you can see here, in this case, we can print the structure. We can add multiple LC sort of for fibers. You can see here, this one LC, the other LCE, this is third LCE. So you can see they also kind of for the LCE we used here also has acrylate. The messaging itself is it's acrylate based messaging, so it also shows very good compatibility with our DLP ink. So we have relatively good interface. But one thing in printing the LCE is that LCE, as you extrude it out, showing here as you extrude it, and the ink is actually, the messaging, they're all aligned. But if you have to fix that immediately. If you don't fix it, it will shrink. So even in the DLP print, the LC essentially, as you extrude them out, they are sort of pre-stretched, and so they tend to shrink back. So this is actually making the printing relatively challenging on a DLP printed surface. So here we started the LC on a glass surface. A glass surface relatively dry, so it's very nice. So you can see here, this is the blue color is LCE printed on the glass, and this is the print on the this actually let me see. Right, so this is the LCE printed on the DLP. A little bit messed up here. So this is LCE. We print this color, the blue color. This is LCE print on glass. You can see the LCE actually stay on the glass surface very well. But the problem with when you print the LCE on the DLP ink, the problem there is that the DLP, the photopolymer had the problem with oxygen inhibition. So the polymer addition process, you generate radical. Normally they like oxygen. So if you have oxygen present, and it will not cure ink. Instead, your radical basically just combine with oxygen, then become dead. So that's what we call oxygen inhibition effect. So in our top-down approach, the top layer always being exposed to the air. So you always have this kind of oxygen there. So after printing the surface, the top surface, it's kind of wet and also a little bit tacky. So this actually makes the LCE wouldn't actually stay on the surface very well. So you can see here, if I make my printing speed very low, yes, I can make it roughly just the length of what I want is the same as what I get. But at increase the speed, you can see the LC ink actually contracts significantly, because here I'm trying to print about 50 millimeter long LCE line, but what I actually printed, if I do a 10 millimeter per second moving speed, and the LCE is only 25 millimeter in length, so you actually lose half of the length. Because you lose that length, and then LCE printed at this stage would not give you too much of actuation, because all the aligned messaging just recover back into the isotropic state. Then you do not have much of sort of actuation. So in our case, we try to print LC at relatively low speed, so we can actually make sure LCE is on the substrate. So by doing that, we can create many different kind of structures. So here shows the video shows how we print this flower structures. And we first print LC on the bottom. You can see we're writing the LC on the bottom. And then we put them into the liquid reservoir for the photopolymers. And here shows we shine the lights. We can print the structures of the flower petals using the DLP. And now we're trying to print the next layer. And then we can take it out and print another layer of LC on the top. And the speed actually being accelerated. So after printing, you take it out, you can actually see these actuations. And this one has LC inside, so you just heat it up and you see the flower stuff. And also we can print the kind of crawling robots. In here, we just put LCE in just one line of LCE in this kind of box structures. Then we can, after printing, we certainly need to special design on the height and the tail to give some kind of asymmetric frictional force. But after printing, you can see these guys can start to crawl by itself. And this actually, using this approach, we are also with DIW, this actually gives us lots of capabilities to create different kind of functional structures. So recently, we also tried to looking at shape mirror polymers. And previously, I showed you the DLP printed part. It's just a regular elastomer. We make it soft so LCE can work. But now we're looking at both SMP and the liquid crystal elastomer. And shape mirror polymers, I think Kevin mentioned that before. Just shape mirror polymer is essentially it's a exhibition of a thermomechanical behavior of your many polymers. And essentially, so it's typically we're using glass transition temperature, right? So if you have a polymer that's in glassy state at room temperature, you heat it up, and the polymer becomes rubbery, and then you start to stretch it, and then you cool it down where you maintain the stretching load. And after that, so you sort of increase, you change the mobility of your molecular chain, and so at temperature below the glass transition temperature, the chain does not have mobility, so fix the shape. And if you heat it up again, it just recovers the shape. So basically, a glass transition temperature is a change of the mobility of the chain. So if you look at thermodynamic or polymer physics, so glass transition is a second order phase transition. It's a kinetic event. It's change of mobility. So it has relatively small time dependency. So if your temperature raise, material becomes soft immediately. If you lower down the temperature, without considering heat transfer, if temperature is low, material immediately becomes stiff. But if you look at liquid crystal elastomer, you really have a phase transition because we have a liquid crystal phase at room temperature. As you heat it up, the liquid crystal phase become not aligned, so they become random distributed. So you become isotropic. So you do have a aligned phase and also a random phase. So it is a phase transition process. So it's a first order transition, and we know that if you're first order phase transition, it has very strong time dependency, right? If for example, if you try to freeze water, water will not be freeze immediately. You have to put it in the temperature below 0 degrees C for a certain time in order for your water to become ice, right? So similar here, it is a time-dependent process. So there's a time difference between the transition of shape memory behavior and the liquid crystal elastomer behavior. So here we're trying to utilize this time difference to create interesting structures. So here's the idea: if I can print LC on shape memory polymers, so if I heat it up, and certainly I was heat it up, the SMP becomes soft, and then my LCE start to contract. So this will give me this kind of bending deformation. But if I do a really quick quenching, cool it down, if I do the ambient cooling, if I heat it up and cool it down slowly and gradually, because this actually would just the LCE would drive things back to the original shape. But if I do a quenching in this case, I just quickly cool it down. In this case, SMP will be immediately become stiff. Well, the LCE does not have changed time actually to do this kind of phase transition. So we can actually lock the shape into the high temperature shape. So as I heat it up again, it will become this shape again. So if you do an ambient cooling, it comes back. If you do a quench, it can go this way. So you actually can branching the shape depend on your cooling rate. And so that's what so here shows one the experimental demonstration. So here's a strip with LCE and SMP. Here we're using a thermochromic dye, so in SMP. So when the temperature is up, you can see the color become sort of pink. When you cool it down, become black. So this actually ambient cool, you can see here gradually just the beam actually becomes straight. So now I heat it up again. Right. So now you can see the bending. Now I put in the ice water, and you can see my structure just being fixed in that bent shape. Right. So if you heat it up again, it would just come back again. So you can do this kind of reversibly. Depends on where you want to go. So you can control the heating and cooling history. You can obtain different shapes. And also you can see here we can For example, we can ambient cool it normally is slow, like I said before. I can cool it down maybe for 44 seconds until I reach this shape. I can quench it, then the material will be sort of locked into this shape. So you get lots of flexibility. And also at this shape, because you have shape mirror polymers, so material is actually very stiff. So we can achieve many different structures. Certainly utilize the flexibility offered by the 3D or 4D printing. We can control how we lay the LCE fibers. We can achieve kind of this kind of helical shape, or this kind of saddle shape, or make a coil. Many different shapes. And like I said before, just at a low temperature, the material actually is a shape mirror polymer. Low temperature in glassy state is very stiff. So we can actually, this shape actually can support the load. So in this case, we heat it up, and then we move it to an ice water. You can see here, this one just moving, cooling is not that fast. So you see a little bit recover, but now after that, you take it out, it actually become pretty stiff. So in this case, we can put a 1 kilogram of weight. I think 1 or 2 kilograms of weight. This kind of structure can still support that weight. And when you heat it up, it just comes back. And we certainly, this one, the previous one I can show you, certainly you can make gripper for sub-robotics, but kind of we're making too many grippers. So Devin has a new idea just to come out the idea, so why not we can make a wrench. In this case, actually, we print a wrench, we put the liquid crystal elastomer at this edge, and such that with different kind of cooling, heating rate, we can adjust sort of the opening, the size of opening for the wrench, right? So we can make it a M4 bolt or the M5 bolt, depend on just how fast I cool it. I can change into different shapes. We can make an adjustment, so make a multifunctional wrench in this case. So now let's come back. We have recent work just publishing in Advanced Materials. We try to 3D printing freestanding liquid crystal elastomers. If you look at the previous work done on the liquid crystal elastomer, typically we print on a substrate, right? If you look at this work actually by Jennifer Lewis group, and they print the liquid crystal elastomer on a substrate and give you different actuations. In our previous work on the DIW DLP combined approach, we also print the LC on the regular elastomer substrate. So the advantage that relatively you can easily achieve that printing, and the drawback is always the deformation mode you generate is a bending, right? And DIW, like I said before, it's the most used approach for printing for printing the LCE, and people also try to using this DLP printing approach to print LCE. I think this work is done also by Kevin and also Chris Yakaki's group. But in this case, they're printing the LCE, but the LCE is not really aligned, so they're really using the LCE for energy absorption. And the other approach really by Rob Shepard group, and they're actually using this kind of old DLP approach. This actually B9 creators approach. That's before carbon, the DLP printing essentially, and they try to do the shear, try to separate the printing the layer from the substrate to do the shear. So they're actually using this shearing approach to align the LCE. But still, in this case, your LCE is only can actuate in one direction. So I challenged my student Xirui Peng, and who just defined his thesis. And so we asked him, can we do a printing in the air, right? So just to do a freestanding printing. So we're using our DLP and DIW approach. So here's basically the setup. We have a DLP resin. We try to print some either support structure or sacrificial structures. And then we try to write the LCE line in the air. In this case, we need to overcome several challenges. And first of all, just because I have both the DLP ink as well as the liquid crystal elastomer ink, and I have lasers that's going on all the time because we just use about this laser point, they're on during the printing all the time. So we want to avoid interference between the laser and the DLP reservoir, because you don't want the laser to cure the DLP during the printing. So in this case, we pick a laser, we're using a 450 nanometer laser, and then we're using this for the LC, we also pick a photo initiator that's a PI 784, has a sort of a absorption cover between 300 to 450 nanometer resin. So the laser would cure this one, the LC. But if you look at for the DLP resin, we're using the photo initiator that is A19, which is typical people use. And A19 actually, if you look at the photo absorption spectrum, it actually would not absorb light at 450 nanometer. So that means if I shine the light to the laser to the liquid resin, it will not cure the resin. In addition, we put the Sudan 1, which is typical photo absorber. And also, Sudan 1 actually has a peak absorption at 550 nanometers. So even your light goes to the DLP resin vat, actually everything basically just being absorbed by the Sudan 1. It also will not cause the curing. And the second one, just we need to really cure the resin fast, the liquid crystal elastomer really fast. So in this case, we also put another cross-linker, which is it's PETA. The T actually means it triacrylate. So TA means triacrylate. So the triacrylate can cure really fast. And in addition to avoid, because my DLP nozzle need to move in the space, so we actually put four lasers such that we can have unblocked cure of the printed resin. So here shows the experimental setup that she reviewed. And here shows the printing process. This is one line. We actually did a study at different printing speed. And here shows we're printing a line between two sort of a support at different printing speed. Right, this is the last one is 20 millimeter per minute moving speed. So after printing, we can just demonstrate actuation. We just cut it and attach a small nuts to it, and you can see the actuations at the different printing speeds. So you can see here, the interesting thing is that at roughly about 80 millimeter, 60 millimeter, 100 millimeter above, the alignment start to saturate. But certainly, the higher printing speed actually gives you some alignment. So we actually did quite a thorough study on this. So the idea is actually we want to print very fast, because as we extrude it out, the liquid, the messaging being is aligned, but the probably not aligned to a significant amount. So what the Siri did actually, we try to move the nozzle really fast. So the alignment, the printed filament will be stretched, and then after being stretching, you further align the messaging, and then you shine the light, you cure it. So it's really a combination of extrusion, alignment, and also the printing speed mismatch causing alignment. And you can see here, but certainly as you move too fast and you basically most of your messaging being aligned, then you can sort of gradually just lose the gain that you have. But you can see here, roughly we can achieve about 50% shrinkage, which is pretty close to most of people obtain by just printing on the substrate. Typically, people achieve about 50%. So we're kind of very pretty good in terms of actuation we can achieve. And with this capability, we can print lots of interesting structures. This one we actually print sort of a circular lattice. So you can see here, that's what we print. We print LCE first. And then you start to do the DLP print. You just add different DLP layers. And after that, you take it out, you can add another LCE layers. So now you can do the actuation directly after print. You can take it out, you heat it up, it would just do this kind of contraction in the plane contraction. And like I said before, we did the tensegrity. In this approach, as mentioned, we print shimmer polymers by the object 3D printing. This is the white part, that's by object 3D printing. And then we also print this kind of polyurethane fibers using this FDM, then we assemble that. So that was 5 years ago. Then at that time, my dream just can we directly 3D print. Here shows the assembly process, right? We print this one, then we just put them together. So it's kind of pretty tedious. And so at that time, thinking, can we directly print this tensegrity? So actually, Siri did it. So you can see here, and this is our design. And so here he actually print the first bottom layer of the liquid crystal elastomers. And then he print this sort of the rods. In this case, he actually make the rods to be very stiff, because you can see here this, when you take it out, this rod is actually very slanted. And so you really need a very stiff material to, otherwise this rod will not support its own weight. So now he printed everything on it. And then you can achieve this actuation, just take it out after print. And we can also print the freestanding actuators. In this case, we can print a structure. This structure, essentially, it's a square structure. We put some kind of loose joints at the edge. In this case, because they're so loose, so they could not support its own weight. So after you print, it just, put the weight on, it just fall down. So in this case, we also print this kind of liquid crystal elastomers, to it. So as we heat it up, the liquid crystal elastomers shrink such that increase the stiffness of the structure, so make the structure stand out. So in this case, actually, it's very interesting. Here, actually print this. You can see this wire is actually, this wire here, you can see it is actually very loosely contacted. So what Shiri did, actually, he printed, not in the plane, he actually printed up. And after printing, he dropped it down. So the length actually would be, this length would be longer than this one, such that when you print, it's still kind of very loose structure. Then when you heat, it will just pop it up. We can also print a 3D lattice. This is a 3-dimensional pyramid on the surface. In this case, we're using a dissolvable DLP ink. So we first printed a DLP structures, first support structure with using the DLP, and this got rods. And then he write this kind of LC on top. He write this LC on the top. And after this printing, he take it out, put this structure in water for 4 hours, and the DLP printed part would just be dissolved away. And after that, you got the freestanding pyramid structures. When you heat it up, it just comes down. When you cool it down, it just comes back. You can do this repeatedly. We can certainly create some kind of functional structure. Like I said before, the actuation of LC also depends on your printing speed, right? So in this case, we're using higher printing speed on this side, lower printing speed on this side. So this side will give you a higher amount of actuation. This one give you a lower amount of actuation. So we can actually create a lattice that actually have a kind of a gradient of actuation. In this case, we can put a glass slide and put a roller on top. And you can see here as we heat it up, and this roller just tilted, and the glass slide just tilted, and basically let the roller roll away. And this actually can have some interesting functionalities. So in summary, just multi-material additive manufacturing offers great opportunity for 4D printing, and hybrid multi-material additive manufacturing has the advantage of more diversified material choices and also more diverse type of structures. We integrate DIW with DLP. Using DLP print the box structures, and DIW can add functional components. I think this is more important. Just conductive ink and liquid crystal elastomers, adding that you could really increase your design space for 4D printing a lot. And more importantly, this is actually low cost. You can probably build this one in less than I would say 10,000. That's for sure. Maybe even your type bar, they probably can build in $5,000. So that's another advantage here. So I'm going to stop here. Thank you.